Hello. Okay, so we're going to go ahead and get started. This is still going to be a bit of a review for you guys, but I think it's necessary because a lot of you struggled with this when you learned it last year. So we're going to start with exponential and radical expressions. As I said before, this will be a review. So if you remember it, awesome. Then you're going to fly through the homework and you're going to do wonderful. If not, this will be a nice little refresher for you. So today we're going to do exponents and then tomorrow will be radicals. So let's just review. So exponents are simply products written, products of a real number times itself n number of times. So it's usually written with a base and then an exponent that just indicates how many times we're multiplying that base by itself. It is often just referred to as the nth power of some base a, or a to the n power, where again a is the base or the number we're multiplying, and n is the exponent or the number of times that we're multiplying that base by itself. So some examples that we have: 5 to the power of 4 would be the base 5 multiplied by itself 4 times, so 5 times 5 times 5 times 5, and that equals 625. The base does not have to be a whole number. For example, I have 1/2 to the 5th power, or 1/2 to the power of 5. And that base 1/2 is when I multiply by itself 5 times, which leaves me with 1 over 2 to the 5th power, because 1 to the 5th power is still just 1. 2 to the 5th power is 32, and I get 1 over 32 as my answer. Our base also does not have to be positive. So I have -3 to the power of 3. So I do -3 times -3 times -3. -3 times -3 is positive, but then you multiply by a negative again and it gives you a negative answer. If you were to just put in your calculator -3 to the 3rd power, or -3 squared, or -3 to the 4th, without any of these parentheses, I cannot guarantee that your calculator will give you the correct answer. Okay, it's very important that when we're using negatives, we are always using parentheses. Same thing with fractions here. Okay, because if you had 2 over 5 to the 5th and you didn't use parentheses, then you're not taking the entire thing to the exponent that it's required to go to or needing to go to. Okay, so when in doubt, please, please, please always use parentheses when you're plugging into a calculator. The good news is you're really not going to be using a calculator that much, especially not on assessments this first half of the year. So I guess I don't have to worry too much about that. So here's another example where I put the negative and the fraction together. So I have the fraction -1/3, all taken to the 4th power. Again, here -1/3 is our base, 4 is our exponent. So I did -1/3 times itself 4 times, which is the same as taking the numerator to the power of 4 over the denominator to the power of 4, and I just simplified the fraction. This also works when I have a coefficient in front of my base and exponent. I still do it the exact same way. I do the base to the however many times the exponent was listed. So I had 2 to the power of 3 here. So I did the base 2 3 times. And then I multiplied that by the coefficient 5 that was out front. You always do the base and exponent before we multiply by the coefficient out front. If you want to work through some more examples, they're there for you. Here's just another caution when you're using a calculator. Please, please, please always use parentheses. Here are a couple rules. Actually, these are all of our exponent laws and rules. These should be review for you. If they're not, please study them, look at them, practice them, because you're really going to have to know these by heart. Okay, these are some things that you shouldn't have to write down or have in a notebook to remember. Eventually, you should just know them off the top of your head. The first thing is any base to the power of 0 is 1. It doesn't matter if that base is -676 or if it's 2. It's always going to be equal to 1 when taken to an exponent of 0. Okay, so here I have the example 3 to the power of 0 equals 1, but so does the negative of the square root of 2 to the power of 0, because anything to the power of 0 is 1. Also, anything to a negative exponent means that that base and exponent need to move across the fraction. So if we have just a base to a negative exponent, that's the same as 1 over that base to the positive exponent. Okay, so here's an example. If I have 5 to the negative 3 power, that's the same as 1 over 5 to the positive 3 power. So that 5 and 3 moved across the fraction bar into the denominator. Here's another example, negative 3 to the negative 5th power. That negative 5 right there means that we need to move across the fraction bar into the denominator. When I do that, the negative 5 becomes a positive 5 and my base stays the same. So I have 1 over negative 3 to the power of 5. Some other laws, and I have some examples of each of these, are if I multiply the same base with different exponents together, I do that base to the power of exponent plus exponent. So when we multiply bases, we add exponents. If I take a base and exponent and raise it to another exponent, it is the same as that base to the power of the exponents multiplied together. Okay, so when we raise a power to a power, we multiply the exponents together to get our new exponent. If we just multiply our bases together, then we add our exponents. If I have two bases or two numbers or two variables inside of a parentheses and I take both of them to the n power, that just means that is the same as taking each of them individually to the nth power and then multiplying them together. So here I have a, b, all to the power of n. That's the same as a to the power of n times b to the power of n. If I have a fraction, same thing. The numerator to the power of n over the denominator to the power of n. If I have a fraction, say a to the m over a to the n, that's the same as subtracting your exponents. I will tell you that it's best to do the subtraction by moving to wherever the largest exponent is. Okay, so if I have a to the m over a to the n, I'm assuming m is larger than n, so it becomes a to the m minus n. This is the same, however, as if I had moved the m down, and it becomes 1 over a to the n minus m. Those are the exact same. So it technically does not matter which exponent you move where, as long as you stay consistent and you follow all the rules. Okay? And then here's just another subtraction example. Okay? And over here I have actual numerical examples. If you're not comfortable with any of these laws, please work through them and do the example and practice it. Okay? So here are just some other examples that apply the laws. We're actually going to go ahead and talk through all of these just so you have these as a reference. And then this should be enough to do your homework. Okay? So on this first example, I have x to the 5th times x to the 6th times x squared. The good news is all of these have the same base, so I know I can use my exponent law that says if I multiply same base, then I add the exponents. So this is the same as x to the power of 5 plus 6 plus 2, which is 13. So my answer is x to the 13th. This next one, I have 3 times s times t, all to the power of 4. So that just means I'm taking each of these individually to the power of 4 and putting the answers together. So this becomes 3 to the power of 4 times s to the power of 4 times t to the power of 4. If I don't know what the variable is, I can't really simplify it at all, but I could simplify the 3 to the 4th power, which is 81. So my final answer is 81 s to the 4th t to the 4th. This third example right here, I have c to the 8th over c cubed, which is to the 3rd. 8 is bigger, so I'm going to subtract the 3 up. So it becomes c to the power of 8 minus 3. 8 minus 3 is 5, and I keep my base c. Fourth example, y to the 5th, all raised to the 7th power. Remember, when we raise a power to a power or an exponent to an exponent, we multiply the exponents together. So this becomes y to the power of 5 times 7, which is 35. We're going to go ahead and jump up here to the top of the second column, and then we'll come back to that last one in the first column. So this is p over 2, all to the 5th power. This is the same as taking the numerator to the fifth power over the denominator to the fifth power. So it becomes p to the fifth over 2 to the fifth. I can't simplify p to the fifth at all, but 2 to the fifth is 32, so I go ahead and put that in. U cubed over u to the eighth. Again, I like to move to wherever the largest exponent already is. So 8 is bigger than 3, so I'm going to move the 3 down. Since I always have to have something in my numerator, I just go ahead and put a 1 there. And it becomes 1 over u to the 8 minus 3. Remember, when we have a fraction, we subtract exponents. 8 minus 3 is 5, so it becomes 1 over u to the fifth. On this one, we're just going to go ahead and multiply like terms. So I do 3 times 4 to get 12. X cubed times x. Remember, when we multiply, we add exponents. So this is a 3 and that's a 1, which gives us 4. And I do y to the fourth times y to the fifth. 4 plus 5 is 9. On the next one, again, I distribute this exponent 4 to everything inside the parentheses. 2 to the fourth is 16. A squared to the fourth power is a to the 2 times 4, which is 8. B cubed to the fourth power becomes b12. And c to the fourth power is just c to the fourth power. This one looks really confusing, but it's not too bad. It's just like this previous problem where we distribute the exponent and then combine like terms. So I'm going to go ahead and square this first parentheses first. 2 squared is 4. R cubed squared becomes R6. And S squared is S squared. I do the same thing on this one, distributing the 3. So S cubed is S cubed. R cubed cubed again becomes R to the 3 times 3, which is 9. And just multiply straight across. So the 4 stays, the R6 stays, and then the S cubed joins those. Then I have S squared and R9. Now my last step is to combine across the fraction bar. So again, we leave the largest exponent and then move the smaller one and subtract it. So the 4 stays because I can't do anything with that. But then I have an S cubed and an S squared. Cubed is bigger, so I move the S squared up and I get S to the power of 3 minus 2, which is 1. And then I have R6 and R9. 9 is bigger, so I move the 6 down and subtract it. R to the 9 minus 6 is R cubed. And that gives me my final answer there. Then I go ahead and move over here. So this again is a parentheses raised to an exponent, so I go ahead and distribute the exponent. U to the negative 2 to the negative 3 becomes u to the negative 2 times negative 3, which is positive 6. V cubed to the power of negative 3 is v to the power of 3 times negative 3, which is negative 9. I can't leave a negative exponent, so that has to go ahead and move across the fraction. So the u6 stays up top, and the v negative 9 becomes v positive 9 in the denominator. And again, this just reaffirms that if I have a negative exponent, it moves across the fraction bar. Same thing if I'm taking a fraction to a negative exponent. I can just flip the fraction and then make the exponent positive, and then I can distribute it in. And here are some examples that you can work through. If you need some additional examples, please let me know, but the internet has tons of them. And then we're going to do some more of this and then exponents tomorrow. So your homework today, I believe, is 1 through 32, just doing the odds. And then you're going to keep that homework and you're going to add to it tomorrow when you do another set of problems. Okay, so make sure you're hanging on to that. So this homework that you're given today is going to be due on Wednesday because you're just going to add to it tomorrow. Okay, have a great day.